So today we are going to start the next part of nuclear physics. In our earlier topics, we discussed about the general properties of nucleus. We started with what actually a nucleus consists of. Actually, what a nucleus consists of, or constituents of nucleus, and their basic properties. And subsequent lectures, we discussed about the size of nucleus, mass of nucleus, charge of nucleus, density of nucleus, and in detail about the mass defect and binding energy, particularly average binding energy per nucleon against mass number curve. We also seen about the angular momentum of nucleus, parity, magnetic moment, and electric moment. So in this part of the lecture, that is after completing first unit, we have completed the first unit, we are moving to second chapter, that is unit 2, where we will be discussing about nuclear models of nucleus. Basically, two important models for nucleus, that is liquid drop model and shell model. So in liquid drop model, so we will see the details about the analogy between a drop of liquid and a nucleus. We also discuss the semi-empirical mass formula, and we will discuss about the significance of different contributions to binding energy. Thereby, we will discuss the stability of the nucleus. And we start the class with a nuclear force. We will try to understand the concept of nuclear force. We will try to understand the characteristics, properties of nucleus, and at the end, we will see about how Yukawa's meson theory. So in this curve, you have already explained, that is average binding energy against a mass number. Along y-axis, we have binding energy, average binding energy, and along x-axis, we have mass numbers 0, 50, 100, 150, 200, 250. Why I am repeating is, the interesting part of this is, as the mass number increases, see, from 0, 1, 2, 3, 4, 10, 20, 30, 40, 50, 100, 150, 200, 250. So if you look at the average binding energy, first it is increasing, then there are some peaks, and the average maximum is for iron, that is 8.8, and for higher mass numbers above 200, it decreases to 7.6. The major part of binding energy curve, that is from mass number 40 A equal to 40 to 160, the curve is almost flat, and which implies that for mass numbers 40 mass number, that is A is equal to 40 to A is equal to 160 and above. So for the very broad spectrum of mass number 40 to 160, what is happening? Binding energy is almost constant. Average binding energy, that is binding energy divided by mass number, is constant. It is almost 8.8 MeV. Therefore, the curve is flat from here to here. So which means that as you move from 50 onwards up to 200, you go on adding the nucleons to the nucleus. When the number A increases, its binding energy increases, but average binding energy average binding energy remains constant. This is what we will be seeing in the today's concept. So, nuclear force. So, we know that inside the nucleus is, see, you look at this diagram, nucleus is very small in the very small region, and you also know that its dimension is 10 to the power of minus 15 meters, or 1 or 2 Fermi. It is 1 Fermi or 2 Fermi, the very small region. So in this very small region, in the small region of nucleus, there are protons and neutrons. The blue ones are neutrons, the red ones are the protons. So neutrons or protons are placed in a very small region. So you can also see that there are two protons very close to each other. There are two neutrons close to each other. There is a neutron and a proton also tied together. So there is something which is very strong, because you know that if two protons are positively charged, this is what you should understand. Two protons are positively charged. If two protons are brought together, then you know that there is an electrostatic force of repulsion. So according to Coulomb's law, there must be a repulsion between the two protons, but it is not so. They are placed in a small region. Similarly, two neutrons and one neutron and one proton. Why this is happening is because of, when we can place two like charges together, that is by applying a force. So therefore, inside a nucleus, inside the small region of nucleus, that is 10 raised to minus 15 meters, or 1 Fermi or 2 Fermi, many protons and neutrons are placed together by a force which should be very strong force, and this force is a nuclear force. That is what we are going to study now. So since nuclei are stable, many nuclei are stable, and there must be certain force between nucleons, that is protons and neutrons together, we call them as nucleons. It binds them together. Such a force is a nuclear force. Now you can see how a nuclear force should be. The nuclear force is a force, it acts between protons and neutrons. So you have shown you here blue and red. It acts between two neutrons and it acts between two protons. The nuclear force is a force that binds protons and neutrons in a nucleus together. This force exists between two protons, neutron and proton, or two neutrons, which is represented by an interaction between PP, or two protons, N, that is two neutrons, or NP, one proton and one neutron. In all these cases, see, this is very important. In all these cases, nuclear force is attractive. It has to be attractive. Otherwise, there would not be stability of the nucleus. Because nucleus is stable, in its stable state, all these forces between two protons, between two neutrons, or a proton and a neutron are all attractive because of the nuclear force. Therefore, nuclear force due to interaction between proton and proton, between proton and proton, or between neutron and neutron, or a neutron and a proton is the same. It is always attractive in nature, and it is very strong because it has to overcome the Coulomb's force. Repulsion between two protons is overcome by applying a very strong force. We can bring them together. So this very nature of nuclear force is very strong. It is stronger than the Coulomb force by 10 to the power 31 times stronger than Coulomb force. So you can see the magnitude of nuclear force. It is very large. Therefore, two like charges are brought together. So two protons which are positively charged are placed in a small region by application of nuclear force, because it is very large, it is overcoming the Coulomb repulsion between the two protons. Similarly, it is greater than the gravitational force 10 to the power 27 times. It only means to say that the nuclear force is very strong force. See, nuclear force is strong force. It is responsible for holding the nucleons of a nucleus together, that is protons and neutrons. Protons and neutrons of a nucleus together. So holding the protons and neutrons of a nucleus together, and it is always attractive in nature, whether the force is between two protons or the force is between two neutrons or it is between neutron and a proton. Therefore, the nuclear force is a very strong force. It is greater than Coulomb force, it is greater than gravitational force, it is a strong force, and it is always attractive in nature. This nuclear force was first discovered by a Japanese physicist Yukawa, Hideki Yukawa, H. Yukawa, in the year 1936, wherein he first discovered a new particle. He discovered a new particle, meson, mu meson, in the year 1936. And what Yukawa said, which we will be seeing in the subsequent slides, is that the nuclear force, so we know that from our basic knowledge of physics, that for every force there must be an origin. So it should start from some point, and for the reason for the source for this force is the exchange phenomena, which we will be discussing in the next slide. And further, in the year 1947, a pi meson, another kind of meson, pi meson, was discovered, and Yukawa was awarded Nobel Prize for his discovery of nuclear force in the year 1949. So the basic characteristics of nuclear force are the nuclear force, how nuclear force is. So we have just now understood that nuclear force, it cannot be like Coulomb force, because Coulomb force is sometimes attractive when it is between two like charges, and sometimes it is repulsive when it is between the like charges, and attractive when it is unlike charges, that is positive there will be repulsion, negative and positive there will be attraction. Whereas nuclear force is always attractive, whether it is between two protons which are positively charged or between two neutrons or a proton and a neutron, and they must be strong so that they should hold all the nucleons of a nucleus together. First characteristics of nuclear force is saturation. The nuclear forces are short range. The range of nuclear force is short range and saturated. How to understand short range? Because the nuclear forces act inside the nucleus, and the nuclear range itself is very small. So you know that if this is a nucleus, then the diameter itself is 10 raised to minus 15. Radius is 1 into 10 raised to minus 15. At the most, diameter can be 2 into 10 raised to minus 15. So there can be maximum of 2 Fermis or 1 Fermi or 2 Fermi or 2 into 10 raised to minus 15 meter. So nuclear force has to work in this region. The nuclear force has to work in this region. Therefore, the dimension of nucleus itself is small. Therefore, the range of nuclear force is small. So the nuclear forces are short range. It means if a proton is here you can say again same color code you can refer. So the red ones are protons and these are neutrons. Then two protons or two neutrons or any a proton and a neutron. This neutron can have interaction with this, with this, with this, with this, and with this. So it means there can be an interaction between the neighboring nucleons. Neighboring nucleons. This has no effect on the nucleon which is far away. It means though in a small region, the nuclear forces are short range. They work up to only a certain distance of 10 raised to minus 15 meters. And if you draw a sphere with this as a radius, you can draw a circle, but it is 3 dimension. So with 10 raised to minus 15 as a 10 raised to minus 15 as a radius, then if you draw, you get a sphere, and this is known as the action sphere, sphere of action, sphere of influence of the nucleus. So the neutrons and protons or the nuclear force has a action in this distance only. Therefore the nuclear forces are short range. They can act only up to the next neighboring nuclei, and they don't have effect on the nuclei which are very far from them. So therefore nuclear force disappears at a distance greater than 10 raised to minus 15. Outside this range, there is no effect of nuclear force. Therefore nuclear forces are short range and they are saturated. You can also look at this graph. This is a nucleon. This is the nuclear distance. 1 unit, 2 unit, 3 unit, 4 units. That is 1 Fermi, 2 Fermi, 3 Fermi, 4 Fermi. That is nuclear separation between two nucleons. So you can see that when the two nucleons are in the nuclear range up to 1 or 2 Fermis, the nuclear force is very strong. And if you go away, then it decreases, and at very far distance, so there is no effect of nuclear force. Whereas the electrostatic force, so you can see that, so as it approaches, there is increase and it decreases with a distance. So you can look at this graph and conclude that the nuclear forces are short range because they work only on the neighboring nuclei, where the maximum distance is 10 raised to minus 15 meter. Beyond 10 raised to minus 15 or greater than nuclear radius, the nuclear force disappears, it has no effect. Now this force is originated. How the force comes into existence is because of exchange of a particle. So we'll come to it later. The next property is nuclear forces are charge independent. So nuclear forces are charge independent. Nuclear forces are charge independent. It means whether the force is between two neutrons or two protons or between a proton and a neutron. Between proton and neutron, it is same. That is pp interaction, nn interaction, and np interaction are same. Therefore nuclear force is always attractive. It is independent of charge of particles. Force between two protons which are positively charged, force between two neutrons which are neutral, force between a neutron and proton are always strong and always same. Therefore nuclear forces are charge independent, but they are spin dependent. This is very important difference of nuclear force. They are independent of charge, but they depend on spin. They are spin dependent and charge independent. This has to be made very, very clear. So what do we mean by spin dependence? See, according to Pauli's exclusion principle, it can be applied to the protons and neutrons also. So two protons, two neutrons, one neutron and a proton. So if you want to place two protons in one place, in one level, then both with spin up is not possible. Proton with spin up, another proton with spin up is not possible. One can be spin up, another can be spin down. So two such protons are differentiated by their spin. Similarly, if you want to place two neutrons, one neutron with spin up, another with neutron spin down. So this kind of spin up and spin down arrangement is known as anti-parallel spin. Parallel spin is both same direction. So parallel spin, nuclear force originated due to interaction of parallel spin is greater than this anti-parallel spin. So when a parallel spin is possible, one neutron with spin up, another proton with spin up is possible. You cannot have two neutrons with spin up or spin down, or two protons with same spin, because Pauli's exclusion principle excludes two identical nucleons to be in the same place, whereas it allows one neutron and one proton. They are different, but their spins are same. So this kind of spin arrangement interaction is very, very stable, and it is stronger than the PP and NN arrangement. So therefore, the nuclear force originated out of NP interaction, that is both spin up and parallel spin, is stronger than PP when spin up spin down to NN spin up spin down anti-parallel spin. So parallel spin is stronger than anti-parallel. Therefore, nuclear forces are spin dependent, charge independent, saturated and short range. So you can further add to understand saturation. Again, therefore I made a remark of this binding energy curve. So to understand the saturation, first see that the nuclear forces, we suppose that nuclear forces are unsaturated. We know that they are saturated, but we will start with a statement, contradictory statement, that nuclear forces are unsaturated. What do we mean by unsaturated is, inside the nucleus, if there are a number of nucleons, that is protons plus neutrons, it may be 2 protons, 2 neutrons, or 20 protons, 20 neutrons, or 50 protons, 50 neutrons, whatever it is. So that is a total number of nucleons. So if they are unsaturated, if the nuclear force is unsaturated, then the force coming out because of keeping all A nucleons inside the nucleus, if it is unsaturated, then what kind of interaction will be there? There will be an interaction of A with A minus 1, that is 1 to 2, 1 to 3, 3 to 4, 4 to 5, like this. One nucleon will have interaction with remaining A minus 1 nuclei. A nucleon will have interaction with A minus 1 nucleon. So in this case, unsaturated means reverse is also true, that A 1 with 2, 2 with 1. In this case, it will be counted twice. Therefore, we divide it by 2. So therefore, binding energy is proportional to A into A minus 1 interaction divided by 2. This you have to understand. Suppose nuclear forces are unsaturated. We know that they are saturated. So we start with a contradictory statement that nuclear forces are unsaturated. It means that every nuclei will have effect with every other nuclei. So we count it 2 times, 1 with 2, 2 with 1. Therefore, we divide it by 2. Then the expression comes out to be binding energy is proportional to A into A minus 1 by 2. So if we expand this, first term will be A square. Then binding energy comes out to be A square. So if we start with nuclear force as unsaturated, then there will be A into A minus 1 divided by 2 interactions, and first term comes out to be A square. If nuclear forces are unsaturated, then binding energy will be proportional to A square. Whereas if you look from our studies that from 40 to 160 the binding energy is constant, it means that binding energy is constant 8.8 MeV, or binding energy is proportional to A, not A square. Binding energy is proportional to A but not A square, because from 40 to 160 it is constant and it is coming out to be 8.8 MeV from this curve, which implies that binding energy is proportional to A but not A square. It means that if it is unsaturated, then it should have been A square, but it is A. It means that nuclear forces are saturated. So this is how you should interpret. So far we have seen the very strong nature of nuclear force, that is, nuclear force has to be very strong because it has to keep the nucleons of a nucleus together in a very small region. It should be always attractive, whether it is between two positively charged protons or two neutral neutrons or a proton and a neutron. In all the cases, it has to be attractive and it has to be very strong, that for heavy nuclei, very large number of protons and neutrons are to be placed in a very small region of 1 or 2 Fermis. So hence nuclear force is very strong, it is always attractive, so it is always attractive, so it is saturated and it is short range. It acts over a very nuclear distance, short distance, and it is charge independent and it depends on spin. So these are the properties, and this was discovered by Yukawa through a discovery of new particle meson, and Yukawa gave explanation to the nuclear force by, which is also known as meson theory of nuclear force or Yukawa's theory for nuclear force. So what Yukawa tried to interpret is all the nucleons, that is all nucleus of all atoms, they consist of identical cores. Inside the nucleus of every atom, all cores are same, that is, it is neither proton nor neutron. So what is tried to say is all nucleus consists of identical cores surrounded by cloud of one or more meson. A meson, there may be a cloud of some positive charge, which is a proton, cloud of some negative charge, or cloud of some neutral charge, then that may be a neutron. So these three kinds of mesons, that is a positive meson, negative meson, or a neutral meson, are responsible for the protons and neutrons inside a nucleus. The difference between neutron and proton is supposed to be with respect to meson cloud. If the meson cloud inside the nucleus is positively charged, then it is a proton. If it is a neutral, then it is a neutron. Yukawa assumed that the pi meson, this particle pi meson, is exchanged between the nucleons, that is, a proton and neutron are the nucleons, and a proton emits a pi meson, a neutron absorbs the pi meson, neutron emits pi meson, and a proton absorbs pi meson. Therefore, there is an exchange of particle meson between proton and neutron, because of which the force is created. So, force between proton and another, that is one proton and another, one neutron and another, are result of exchange of a neutral particle between two protons and two neutrons. The nuclear force created because of interaction between pp and nn is because of exchange of a neutral pi meson. Pi 0 means it is a neutral meson without any charge. See, a distance between proton, force between proton and neutron is because of pi plus and pi minus. From proton to neutron, neutron to proton, it is pi plus and pi minus. The force between proton and neutron is because of charged meson, that is pi plus and pi minus. So you can see these equations. Neutron, it emits a pi negative pion or pi meson, then neutron becomes a proton. So though it is abstract, so you try to understand this. Neutron gives out a particle pi minus, then it becomes pi, this is a proton, and proton absorbs a negative particle, it becomes a neutron, because plus minus, it is neutral, this is also neutral. Here also no charge, pi plus pi, p plus minus, charge is balanced on either side. So proton emits pi plus positive pion, then it becomes a neutron. Proton emits pi plus and it becomes neutron. A neutron absorbs pi plus and becomes proton. So Yukawa said that continuously proton and neutron are converted from one into the other. When they change their coordinates, when one proton becomes neutron, its coordinates are changed. Proton, when it becomes a neutron, its coordinates are changed. So whenever a neutron, continuously a neutron is converted into a proton and proton is converted into a neutron by emission and absorption of positive and negative pi particle, pi meson particles, then because of the exchange, because of the exchange of this particle, because of exchange of particle, a force is created. Thus, nucleus is attractive between, whether it is between two protons, whether it is between two neutrons, or between two neutron and proton, it is always attractive, and this force is greater than the electrostatic force. And see, as in the electromagnetic field, its particle is photon. You know that bundle of energy. So it is known as quantum of electromagnetic field is photon. Therefore, meson is the quantum of nuclear field. In nuclear field, the basic element is the meson because of exchange of a meson. That is, when a neutron emits pi minus particle, it is converted into a proton. When proton absorbs pi minus particle, it becomes a neutron. When proton emits pi plus particle, it becomes neutron. And when it neutron absorbs pi plus, it becomes proton. So Yukawa said that continuously neutron becomes proton, proton becomes neutron by emission of pi minus and pi plus particles. Therefore, the interaction is always strong between two particles because of exchange of particles. See, I will show you this image and just wait for 2 minutes, and till end you look at this. So what is happening? There are two persons, A and B, or X and Y, P or Q, whatever you can name. So both of them are continuously exchanging a ball. It's a volleyball. A is giving it to B, B is throwing it at A. So you just observe carefully, A to B, B to A to B. So they are brought together by exchange of this ball. Because of the exchange from one person to other person, the two persons are placed in same place. Just observe. See, if you replace them by two particles, say one proton and another proton, or one neutron and another proton, because of exchange of a meson like this ball, so these two will be bound together or placed together. So a force is created between the two. So this force is the nuclear force, and this nuclear force is created because exchange of a particle, that is the meson. Here also you can see that by exchanging a ball between the two persons, actually if you throw this side, so your force is acting away from this. When this person throws this side, force is acting outside. But actually, though the force is repulsive, but it is creating the two persons in binding them in a small region because of continuous exchange. This word is important, continuous exchange. If there is continuous exchange, then the two persons will not leave the place. This, he will be here, he will be here, then there will be a continuous exchange. So exchange of ball. Similarly, force is created due to exchange phenomena, that is inside the nucleus also force is created due to the exchange of a meson. Liquid drop model. So we'll just introduce today, and in detail we will be discussing in the tomorrow's class. So we have understood about the nucleus. So what we know about nucleus? Inside the nucleus there are protons and neutrons. So protons and neutrons are together called as nucleons. Protons and neutrons are called as nucleons. And we have seen that there is a force to keep the nucleons of a nucleus intact inside a very small region. The dimension of the nucleus is small, and the number of like charges or the number of nucleons inside a nucleus is very large as we move from the heavy mass numbers. Therefore, there must be a strong force to keep all these nucleons inside a nucleus. The precise nature of this force inside the nucleus is not known because nucleus itself is very small, so it cannot be made a direct experimental object. So therefore we have to understand the nature of force by analogy. We use a word, analogy means comparison. So we compare the nucleus with a drop of liquid. So we know that we can very easily study the drop of liquid, its shape, what are the forces acting, how are the forces acting. Same thing we can compare with a nucleus which we cannot see, and try to compare the properties of a drop of liquid and nucleus, and a model was proposed on these studies, analogy between a drop of liquid and the nucleus, that is called liquid drop model of nucleus. In the liquid drop model, this liquid drop model was proposed by Bohr, Niels Bohr in the year 1936, and it was further developed by Wheeler. Bohr and Wheeler in the year 1939, who observed that there are certain marked similarities, marked analogy or similarities between atomic nucleus and a drop of liquid. So you may be surprised to see that what are the similarities between the, if you look at a drop of water that is formed on leaf, So you can see that large number of drops. One drop, if you see that, it is spherical in shape. So drop of liquid is spherical in shape. Why? You know that because of force of surface tension. So the force of surface tension, see, the force of surface tension which is acting makes the water drop or a liquid drop spherical in the stable state, and the force of surface tension acts on the surface of the liquid drop. So nucleus is also in the stable state. Nucleus is spherical. As water drop is spherical in shape in the stable state, nucleus is also spherical. As the spherical shape of liquid drop is because of the surface tension. Forces of surface tension act on the surface and on make the drop spherical. Similarly, a potential barrier, because of the positive charged protons, a potential barrier is created on the surface of the nucleus, which makes the nucleus spherical in shape, and it is responsible to make the stable spherical shape of nucleus, similar to forces of surface tension on the surface of a liquid.